Welcome to another CO2 Monday with Trevor. I'm your host, Trevor Matthews, and today I have a special guest, a good friend of mine that I met a few years ago when I used to work at Emerson. Very, very smart gentleman who started in with CO2 probably when I started in the refrigeration industry. And I'm super excited about this conversation because we're going to get into CO2 heat pumps and chillers, which a lot of people don't really understand that it's been around in heat pumps for 20, 30 years. And so I really wanted to bring this guest on to talk about this because he's an expert from around the world. Wynand Groenewald, welcome.
Thanks, appreciate. Glad to be here. Thank you for having me.
Awesome. Why don't we start, Wynand, talk about a little bit about your background, how you got into the industry, and how you got into CO2 refrigeration.
Sure. Yeah, I'll try to keep it short and sweet. Where we can get into the juicy technical stuff. But yeah, I mean myself, I'm a mechanical engineer, and then I did my post grad on CO2 heat pumps. So we both started in the refrigeration industry at the same time. I just got into the industry knowing CO2 and not HFCs. I had to learn HFCs after the fact. So that's always something that I always find quite interesting. So I can really say that I've got a passion for CO2, and I had to learn the rest of the refrigerants after entering the industry by force. So, so yeah, I got started on CO2 heat pumps, and then got involved, based out of South Africa myself, got involved with a company where we designed, manufactured, and basically introduced CO2 into Africa. First started with retail, then moved towards the industrial side of life. So got experience from design, manufacturing, installation, servicing all the way through. And then, yeah, today, full blown trying to introduce CO2 into the market, getting people to get excited about it.
I love that. I love that because it's really important because you've been in this industry for over a decade, learning, training, educating, bettering yourself, talking with people around the world, and it continues to get out there. But it's still such a small industry that we need to talk about it more and more. And I really appreciate it. You started a company called Future Green Now. Why don't you tell us a little bit about your company?
Sure. Yeah, like I said before that, basically all of us worked together before we started FGN. So we decided to break away just over 2 years away, start our own thing, mainly around we wanted to spread the CO2 word, I guess, if you want to call it that way. We felt that we can really make a bigger impact in the industry by sharing our experience, passion, and knowledge around CO2. So today we're a small team, but you can call a consultative CO2 team. Our core competence is CO2 refrigeration, heating, and whatever else you want to do with CO2. So yeah, so I mean, we like it because we can really go ahead and we can do a lot and we can really support people. Like I think I mentioned even to you, is we always say if we do our jobs great, we'll keep on working ourselves out of a job because we want to empower more and more people to go with naturals instead of the HFC based refrigerants. So our expertise or our what we do is anything from product development to full turnkey projects to training to installation design for contractors or product development, anything that helps people take on CO2 and companies transition towards CO2 as a refrigerant, and
Yeah,
on an international basis. So although we're based out of South Africa, we are working from Middle East to Australia to North America to Africa, so
I love
covering
that.
the globe.
I love that because, one of the big things I've heard so many times, well, you can't put a CO2 system where it's warm, where it's our high ambient. And you just said many countries that it's like the hottest places in the world, and you're in there and involved in developing systems with other contractors, engineers, and even manufacturers, because I know that you work with a broad base of the industry's best. So I love that. Let's get into it. Let's talk about CO2 heat pumps. What are CO2 heat pumps? And let's give an introduction to that.
Sure. Well, okay, yeah, CO2 heat pumps is basically, I think in a nutshell, it's similar to it's a refrigeration cycle. So basically, we always say we're moving heat. We're not making something cold. We're actually removing heat the whole time. So in refrigeration, when you're making something cold, you want the room to be cold, you take heat out of that room until you reach the temperature that you want, but you put that heat somewhere else. So a heat pump is, our heat source is the globe. So all our heat that's around us in the atmosphere is an endless supply of heat that we basically take out of the atmosphere, we put it through a vapor compression cycle, and we put it into a medium that's usable for, which can either be air again, or it can be water, or it can be in any means to get to a point where we want to make something hot. So the nice thing about CO2, the biggest difference in a nutshell is the transcritical operation of a CO2 system, where you don't have a pressure temperature correlation anymore. You get a very close approach. You can heat water, you can heat in a single compression cycle without double or two-stage requirements. You can reach heats up to 80 or 180 degrees
Wow.
Celsius and up. So you can really supply high temperatures. So it's good for drying processes and any type of, especially also processing facilities.
That
So
is amazing. 180 degrees Fahrenheit. That's a lot of heat coming from that
yep.
refrigerant.
And
So,
also mostly, like, one thing as well, especially in the transcritical operation, is that one thing people don't, or what you need to understand as well, is that you can reach those temperatures by still taking 100% of your heating capacity out of your system. You don't need to, you don't just use the desuperheating phase of a refrigerant, and you lose a lot of the condensing phase. But because we have no condensing phase when we're operating transcritical, we basically can profile the heat, that we can get everything that's available. Basically everything that we extract from the atmosphere or from the heat source, we can generate and put into the water with as little waste as possible.
oh wow, that's something I didn't know. So that means because it's not condensing, you're getting more efficient from that heat transfer?
Yeah, so I mean, think of it this way: a traditional heating system is basically dependent on your heat supply. Even if you think from a refrigeration point of view, like if you put a refrigeration system outside and you want to reject your heat, your discharge pressure, or where you're operating, is dependent on your heat sink. So depending on how warm or how cold it is, that's going to determine at what discharge pressure you are running. So usually what happens then is that is your condensing, your associated condensing temperature and
Mhm.
pressure. So before you heat that condensing temperature, let's say it is 30 degrees Celsius, for argument's sake. Sorry if I speak Celsius.
That's okay.
Um, so let's say, for argument's sake, that's 30 degrees Celsius. You cannot heat a medium, obviously, warmer than that. So you need to either discharge at a higher discharge pressure to get there, or what you do is you use the desuperheating side of life. So let's say you're desuperheating, your discharge temperature out of your compressor can be 90 degrees Celsius or 100 degrees Celsius or only 70 degrees Celsius, meaning that you can only you can heat your water to a certain temperature, where you will hit a pinch point, which is basically your transition, is where your condensing stops, and then before you go into the desuperheating phase. And then you can try and get as much heat out of that desuperheating phase, where with CO2, we have a high pressure valve in the system, and because we can force the system to run transcritical, which we do in a heat pump system, we have no pressure temperature correlation. So we can determine the discharge pressure of the CO2 system. And because there is no condensing or phase changing on the discharge side of life, that allows us to really create a water profile where you heat your profile and it kind of like follows the CO2. So as you're rejecting heat from your CO2, you're gaining that heat in the water or your heat sink, which gives you the capability to get high temperatures because your pinch point is much smaller, and it allows you to get maximum capacity out of your system, because you do not lose a part of your so-called condensing phase.
Yeah, that is amazing because I know when I talked to some of my buddies that were working on some supermarket transcritical systems, and it was in the middle of winter, and they always say, "Oh, well, you want to be out of a transcritical for to be the most efficient." but they were like, it's -20 out, but we're running in transcritical because we're using heat reclaim. So we are doing preheating of water, and it's more efficient in that area because the energy cost is lower, and they were getting a ton of heat. They were running it into transcritical in the middle of the winter, and I thought that was really cool, a cool concept to do that. So I guess that would all depend on the location you are in the world when you do something like that, and I guess on the supermarket side.
On the supermarket side, yeah, that depends. It depends, like, obviously, yes. Interesting, because funnily enough, I mean, heat reclaim is a benefit of CO2, which basically is a heat pump base. Like, just you get the benefit of cooling something as well. So you double the COP or EER. But then anyway, so the interesting fact is, like, usually when, especially in your colder countries, which definitely Canada is, like, if in the winter when you are at the coldest is when you need the most heat. And there's a misconception, I guess, between running transcritical and running subcritical. If you force yourself to run transcritical versus you need to run transcritical is a big difference.
Mhm.
If you need to run transcritical, that is because your heat sink, the ambient temperature is high. So your gas cooler outlet temperature is as high as your heat sink allow it to be. So I mean, if it's 35 degrees C outside, your gas cooler outlet temperature is I don't know, close to, let's say, 37, 38, or
Mhm.
that's your gas cooler outlet temperature, and your pressure needs to be according to that. So you're running at a high discharge pressure. If you are sitting cold outside, but you force your system to run at 100 bar discharge pressure, which it would be more or less if you're running at 38 gas cooler outlet temperature, your gas cooler outlet temperature does not have to be 38 because you're forcing your system to run at 100 bar. You can still cool your gas cooler outlet all the way to what ambient allows you. So you are forcing your system to run at 100 bar. You're still rejecting your heat to go down to, I don't know, instead of 38 to 20 degrees Celsius, or 25 degrees Celsius, which means you still got all the way to the left of your enthalpy diagram. So when you go into your receiver vessel, you generate very little flash gas. Rough calculations, trying to look at it, basically the penalty you're paying from running your high subcritical to running low transcritical is less than 10%. But if you get that, you would pay in terms of additional power to run at a higher pressure. But if you get 100% heat reclaim, you are getting rid of the requirements for any other heat source within your facility, which either uses gas or power or anything like
Yeah.
that. So you can't beat that. Basically, good heat reclaim out of a CO2 system, you can't beat that with any other technology standing next to it.
Yeah, and that's amazing. That's what's so cool about CO2. All these different things that you don't really think of, because when I think about refrigerants and synthetic refrigerants, they do in one specific thing, or they can do a specific application. Where now with a CO2, you can do all these things in one system potentially, if you wanted to,
Yeah,
which is real cool. Let's talk
you
about some of
should not want to. You should.
yeah, definitely. Let's talk about some of the CO2 heat pump projects you've been on. I know you've been on quite a few different ones, from I'm sure commercial to industrial. Why don't you talk about some of the different projects you've been on?
Yeah, so I mean, we've been we've been involved with heat pumps in the hotel industry, or like, and then also in the retail industry, and then also currently actually busy with a project, heat pump project for space heating applications. So quite a broad sense. I mean, like I said earlier, and also heat reclaim, and as well as chillers with heat reclaim added onto it. So let's say a chiller slash heat pump system, a combined system. So yeah, I mean, all of these kind of operate as a heat pump system. So it depends on how you want to justify or specify a heat pump, I guess. It's a heat pump, generally the term for a heat pump is if you only do heating. So you would have an air source heat pump or a ground source heat pump, meaning that you're not gaining out of the cooling side of life, you're only heating something. So that is straightforward a heat pump. Otherwise, you can look at it as a heat pump with a chiller where you're chilling water, and you create a closed loop system, or like we just mentioned now, heat reclaim onto that system. So yeah, definitely. So interesting stuff. So one main thing about the CO2 system, I guess, if I can put, the, other than the transcritical operation and what we've spoken about now, the benefits of a CO2 heat pump, one of the major differences is, I think, one thing that needs to be understood or and taken into account when using or designing a CO2 heat pump is that the installation side of it is very important as well. Like predominantly HFC based heat pumps that you would look at, they work on what you would call a small delta incremental temperature lift. So basically most of the heat pumps that you get that's either HFC based or something like that, or alternatively based, would do about 5C incremental heating. So you would take it, you will have a storage tank, it doesn't matter, you bring it, you will bring in 20 degrees Celsius, heat it to 25, then 25, 50, all the way to heat the temperature that you require. The one thing with CO2 is to really make a CO2 heat pump efficient, you want to have that system do direct heating. So basically, if you want a storage tank at 60C and your incoming is 25, you don't want to take it incrementally up, you want to go from 25 directly to 60C. So in this, by doing that, what becomes important is your installation side of it, and then also to understand your application. So if you design a closed loop system for food processing or anything where your heating is required, and let's say you don't bring in fresh water or municipal water, then you need to design your application side in such a way that you reject as much as possible heat, so that you can keep that direct lift. Or especially in the hotel industry, or like for domestic hot water, you want to keep good stratification. You want to make sure that you pipe your storage tanks in such a way that you always bring the coldest water to your heat pump and take the hottest water to your tanks and directly to the requirement where it is. So the installation side of a CO2 heat pump does become important.
Yeah, that is very important. I think that's with really any system, but it's more important with CO2 system. And I've been seeing this more and more. What I'm really liking about natural refrigerant, it's making contractors be more cognizant that they need to be doing the things right. There's no cutting corners when you're dealing with CO2 because you can run into a lot more issues a bit quicker. Why don't you talk about some of the issues you've seen with maybe with the installations? One you just mentioned where you need the coldest water coming in and then the hottest water taking it from the hottest place. Why don't you talk about a few other things that you've seen where maybe will help other people?
Yeah, sure. So I guess, yeah, I think the biggest thing is, like, firstly, you need to look at CO2 as just another refrigerant. So the law of thermodynamics and everything that you've known before working as with a refrigerant stays the same. Like, those principles don't go away, because there's one thing that we've learned is a lot of guys that's new to CO2, or a lot of people that's new into CO2, have a standoffish approach to it because the pressures is higher than you're used to. But I think everybody that I've spoken to before, it's always the same outcome at the end of the day, when they say, like, once you understand basically the high pressure valve with the flash gas valve, and once you understand that it's just a refrigerant, it becomes so much easier. And it just really becomes even more fun, I guess, at the end of the day. And then, yeah, I think basically it's just to understand where you're designing if you're going to design your system, you need to design for what your requirements are and for where you are. Whether it's the standstill pressures, do you want the high standstill pressure? So specifically coming back to heat pumps and chillers, predominantly there you would like to design for a high standstill pressure, because you would like your system to cycle off, you would like it to stand still, and you wouldn't want an auxiliary system to basically keep it going. Where with large refrigeration systems, you can get away with lower standstill pressures and maybe a backup auxiliary system if required, because cooling and refrigeration is basically a 24/7 game. But with heat pumps, it's differently. So it's needed to understand what you're designing for and how you can make sure that you get that right. And then I guess when it comes to fault finding, is like I said, the biggest thing is to understand, is to always maintain and always look at the basics. I guess, if I can say, people try to overcomplicate fault finding, and when it comes to CO2, and I think it's literally just keep it simple and keep to the basics. If you're going to look at your pressure and your temperature, if it corresponds when it should be corresponding, and if your system does what it should be doing, you will fault find the same like you would do with any other system.
Awesome. Yeah, and I've been noticing that over the last 5 years, component manufacturers are starting to, make components that can work in CO2, 120 bar, 130 bar for those high standstill pressures. So in heat pump applications, for example, are they all designed for, say, 90 bar or 100 bar, or some of them lower than that? Because as you mentioned, some of that you want to shut them off, right? Are they designed to that high? Mostly.
Predominantly, yes. I mean, your discharge side, you want at 120, 130 bar at least. I mean, 130, in my opinion, is where you want to be on a CO2 system on the discharge side of life. I know in North America, the biggest issue around that is the UL certification of certain projects, certain products. So that's one thing to be cognizant of and to understand is, especially from our side, we came from outside, where we used to all the European suppliers operating at 100, putting your hands on 130 bar design pressure was fairly easy. But all those componentry that we used to use is basically being derated because of pressure requirements in the North American market. So that was quite interesting to know, and good to understand, or good to understand when you're designing your system. So yeah, it's on your high side, you want to go as high as possible. On your lowest side, if you're looking at a heat pump and a chiller side of life, then yes, 90 bar, even 80 bar would be suffice. So basically, it's exactly what we say. It's standstill pressure. So if your system is off and you have heat entering your system, you can only reach ambient temperatures. So what is the pressure corresponding with typical ambient temperatures, and that's what you need to be able to adhere to. I mean, there's other ways to look at it. So also what you can do is it's because of the high pressure differentials. This is much more in refrigeration systems, but I mean also in chillers and heat pumps, is basically just to control your high pressure valves. So I mean, you can easily you can allow your system to isolate. Like if you switch off a heat pump, for argument's sake, you don't need to let it settle like other systems would do, like where you have basically you come there, all the lines are the same pressure. You can isolate your discharge side from your receiver, from your suction side. So you can kind of isolate or break up those pressures where you are. That would make startup easier again. So yeah, that's all small little design details that you can incorporate. But to answer your question, yes, I would say outside, other than industrial applications, where you're starting to look at real large capacities and a lot of heating requirements, meaning that you are running quite a lot, you basically will find that most of the systems are designed at 90 bars, specifically on the domestic side of life. Because you would typically, but funny enough, also that is one tip that I can share as well. I guess it's overall on the heat pump side of life, but I mean, you want the most out of your heat pump, and that means like if you, especially in the hotel industry and the hospitality industry, you've got 2 peak shower sessions in morning and evenings. So you basically want to run your heat pump. You don't want to install a heat pump that's going to take 1 hour to recuperate all the hot water that's required and then be off for 8 hours before it's required again. You want to run it for that 7-8 hours that you want until that water is required again. So you want to run your system as long as possible. So that's what you want to design for as well. But yeah, typically you would look at a 90 bar on the suction side, or
Awesome.
80 bar minimum.
So we've talked about a lot over the last CO2 Mondays about the supermarket CO2 systems, the transcritical systems, to get the high pressure valve and the bypass valve. What extra components in a heat pump maybe compared to one of those, or is it all the same components?
Yeah, so I mean that would be what you depend, like what you design on. So again, you've got various different designs. So you can have a heat pump design that's typically got your high pressure receiver as well. So in that sense, you would have a high pressure valve, you would have a flash gas valve. So that will be, and then you have another additional expansion device that goes into your evaporator. You can have a flooded type system where you've got your discharge line, and you basically your receiver vessel becomes your suction pressure. So that because I mean, in a heat pump or in any refrigeration system, the smaller your compressor differential is, the smaller the pressure differential that your compressor needs to overcome, the more efficient your system. So
Yeah.
typically in a CO2 heat pump, we want to run at high discharge pressure. So the higher the suction, higher we can make the suction, the better for us. So if you have a fluctuating ambient temperature because you have a heat, your ambient is your heat source, you want a closest approach to your ambient condition so that you can have that suction come as high as possible. I mean, another unit that you can look at is you can also look at having your high pressure valve, which usually would, usually your high pressure valve would expand into a receiver. You can have your high pressure valve expand into the evaporator
Mm,
where your heat source is. You can have a low pressure receiver. So in that sense, you do not require a flash gas valve. And you
interesting.
actually running, I guess, then I think in that sense, you're then running a CO2 system as close to a HFC system as you could, where you basically
Yeah.
have one expansion into the evaporator side. You will just have a low pressure receiver or accumulator
Wow.
to allow for vapor. How can I say it? Yeah, you allow for variance in densities and liquid distribution for your system, to make up for that. So, and then bring oil back through that. So that's also something else where you can look. So you want to make it, depending, again, if you want to look, for argument's sake, if you're going to look at EcoCute small domestic heat pumps, you want to keep it as simple as possible. You don't want to overburden the cost of the system.
Yeah.
If you go industrial and you go large, again, there's benefits in having a receiver and having a flooded type system,
Yeah.
over having a small type system. Yeah.
So I've been hearing this more and more that CO2 in the industrial space is going to give ammonia a shot for its money. What's your thoughts on that, like CO2? Because I've seen more and more CO2 going into the industrial base space. What's your thoughts on that?
Yes, I think firstly what you need to understand is how much HFC, sadly enough, is being used in the industrial space.
Mhm.
So CO2 is definitely giving HFC-based industrial applications a run for their money. Secondly, I think ammonia and CO2, there will always be a healthy balance between the two.
Mhm.
So each refrigerant brings its own benefits, and the combination of the two brings alternative benefits. So, I mean, between transcritical booster systems, ammonia CO2 cascade systems, or straight ammonia systems, there will always be an application or a size requirement that suits either refrigerant best. But to answer it, CO2 Mondays, and I'm a very big fan of CO2. Yes, I do think CO2 is slowly but surely making more its way into the industrial side of life. There's a lot of benefits. You can DX. It's non-flammable, non-toxic, low GWP refrigerant, very high volumetric efficiency, very good heat retransfer capabilities, so small piping diameter requirements, reduced installation cost,
Yeah.
um, good heat transfer, and you do not require a secondary medium. I mean, CO2 in most cases can be the secondary medium of certain refrigerants. So if you do not have a secondary medium, you are taking out your losses due to heat transfer, making your system more efficient. It's all about designing around the benefits that you can get out of a CO2 system. If you design around it, then definitely, yeah. I mean, we've been involved with a lot of CO2 industrial applications. It's really fun. It's really great. And there's a lot of benefits that CO2 do bring to the industrial space, and especially when it comes to regulations. Like certain areas, certain spaces are just not made for other refrigerants. Where I mean, as soon as you bring a public, unfortunately for a natural refrigerant, ammonia has got way too much a stronger smell. So I mean, if you introduce ammonia into a public space, you do run the risk of, even if there's a small leak that's not close to lethal, which is rarely the case, if you can smell it very far.
Yeah.
And so yeah, so I do think CO2, it's great because I think there will be a healthy balance but of natural refrigerants in the
Yeah.
industrial space.
Yeah, I love that. And I think so too, because it all depends, like you said, on the design, the application. And that's why you really need to work with your customer and find out exactly what they want. And sometimes they don't know what they want because it's new and you can get so many different benefits. So it's good to talk with your customers about that and educate yourself on what they're looking for, right? Because if you're in a warm ambient, it's going to be different. Like, if you're I'm in Arizona right now. If you're in Arizona designing a system to where I live in Canada, it's going to be two different designs to get the solution you're looking for. So it's good to work with that and understand all that stuff. Why don't
Yeah.
we get into a little bit of the chiller side? Because to be honest, I don't know really anything about CO2 chillers. I know lots about regular HFC chillers or synthetic refrigerant chillers, and I've worked on lots before. But let's talk about CO2 chillers because they're kind of new. Maybe they're not new, but they're starting to be more prevalent. You're hearing more about it in the news and stuff. And I know you've been on some CO2 projects here in North America. Why don't you talk a little bit about CO2 chillers?
Yeah, so I mean, specifically to look at the project that we were involved in North America was in the dairy industry. So definitely there is a big benefit of CO2 which kind of brings this whole topic together. Um, in the dairy industry, basically you are chilling milk, high volumes of milk, and then right after that you need to sterilize and clean your vats. So basically, so the reason why there's such a big requirement, or why I think it's such a good application for CO2 chillers specifically, is that 180F that we spoke about earlier. So while you're making milk cold, you can have this hot water stored that you require. And I mean, you don't need to have either electrical heating to get you there or propane gas to get you there, which at this stage, I mean, one of the main reasons why CO2 heat pumps at this stage is a hot topic, and it filters into chillers as well, is that basically if you look at California and a lot of other spaces, is there is a big move towards phasing out the use of natural gas to heat. The move is towards electrifying it. So, I mean, if you put a CO2 chiller down where there is some heating requirements for your facility, you are not only getting everybody off of your back due to the low GWP refrigerant that you're using, but you're also getting away from having to use additional heating sources or propane gas heating. So you're really like ticking a lot of boxes. So from a chiller side of life, again, it's the same with the heat pumps. There's so many different ways you can do it. Like a benefit, again, like I say, is you can use flooded evaporator type setup, basically where you just maintain a flooded side of life. You get a very close approach. You can again have a very efficient CO2 chiller type of life, or you can go back to, or you can have a DX type system. So yeah, it's a lot similar concepts, I guess. It's defined between, let's say, a refrigeration system or a CO2 chiller, a lot of similarities in the CO2 side of life, on the design side of life, and the approach, which the small nuances and the small changes in between that you just basically take care of.
Yeah. And that's important to understand because once again, it's still a refrigerant and you got to treat it as a refrigerant. There might be some uniqueness, like you said, the higher pressures. You may have to have components that are designed for higher pressures, but it's the same concept. And that's a big industry, the dairy industry for that. I think it's gonna be good to see more of that equipment getting out there because if that is taken on by that industry, that's going to really help grow CO2 in the chiller market, I believe.
Yeah, and I agree, because I mean that's why projects like that are exciting, because predominantly, I mean, in the 15 odd years working with CO2 worldwide, it's every country CO2 is introduced into the market through retail. Then usually naturally the progression is more towards light industrial. And then later on, it's all these other different types of applications. And I mean, we're still very super slow on having CO2 being taken up in the air conditioning sector. But then, yeah, I mean, so basically, I think it's great for projects like that, where breweries and wineries and dairies basically take up CO2 as a refrigerant, and showing that it's beneficial for them to go that route, because that really opens the market for innovative CO2 solutions.
Yeah, no, and I really like that too. Why don't you said something earlier that I would like you to explain to the audience is you said electrification, and that was something new to me a few years ago, and I didn't really understand. Do you want to just explain what electrification is for the people that don't know what that is?
Sure. So basically, I guess, yeah, well, electrification meaning that you do, let's, if we're looking at the heating side of life. So I think 80% more or less of everything that gets made hot in California, for argument's sake, is based off of natural gas. So natural gas burning. So that has a greenhouse gas emission factor towards it. And then basically, so what is happening, a lot of states, countries, um, entities are electrifying their heating and cooling requirements, meaning that whatever you, so sadly enough, putting an element, or what we call a geyser, I don't know what the correct term in North America is for that, if the guys even have that, but in Africa we still have geysers. So that's 100% electrical heating. I mean, you put your COP as one, or for every 1 kilowatt of heating you put in, you get 1 kilowatt of for every 1 kilowatt of power you put in, you get 1 kilowatt of heating out. But meaning electrification is you using electricity to make the heat. With a heat pump, the benefits, if you've got a COP of 4, meaning for every 1 kilowatt of power you put in, you get 4 kilowatts of heating out. So
Yeah.
um, that's why. So when you electrify, that's why heat pumps become such a big part of it, because you can use a quarter of the power that you would require if you went straight electrical. But then everybody would ask why the drive is towards that, is because you can control the grid. As soon as you can make sure your grid is green, you can make sure your state or entity or country is moving towards carbon neutrality, if you're
Wow.
using alternative stuff. So that's why there is a big drive towards electrification of
Yeah.
heating.
Yeah, thanks for doing that because I started hearing it and I wasn't really understanding it at first when I first heard about it, and then it's starting to make more sense that now you're getting not one to one, you're getting 4 to 1. You know what I mean? So you're getting higher COP of it. What is a typical COP on a synthetic refrigerant compared to on a heat pump to CO2? Is there a difference in the COP, or are they similar?
Sure, that's difficult, because that
Yeah.
that depends a lot on the application.
Okay.
Typically, your COP of a CO2 system, your efficiency of a CO2 system is generally much higher than HFC based system. Um, so definitely, and especially if you're looking at the temperature requirements, if you're looking for the high temperature requirements, you are much more efficient than an HFC based refrigerant.
Mhm.
So I know there's a lot of, it depends on applications on the refrigeration side of life when CO2 is more energy efficient and stuff like that. But definitely from a heat pump point of view, CO2 is a lot more energy efficient.
Yeah. Yeah, and it's even like the heat that you can get from it, even the net refrigeration effect, the pounds per hour you can get out of it, it's hands down better than synthetic refrigerants. And you can look that, and
Yeah,
that's something that as a technician I didn't know, but over the years learning more on the engineering side, the design side, understanding enthalpy diagrams, which I highly recommend everybody that's here in that's participating, look that stuff up. It's hard stuff to do, but go and try to understand it a little bit more because it makes a lot of sense. It's like when you look at ammonia, it's like the top refrigerant out there. You know, if you can get the most pounds of BTUs out of it per pound, right? I think it's ammonia, it's the highest one. So it's just to get to understand that stuff. Where do
yeah.
you where do you see the industry going for heat pumps? Because we see like in Japan, there's millions of small residential heat pumps. Where do you see it going over the next, say, 5 to 10 years in more of the commercial and maybe industrial applications for CO2 heat pumps?
So I think efficient heat pumps is to look at, because I mean, you're looking, I think centralized heating makes a lot of sense. And especially with CO2, because the one benefit of CO2, um, put it this way, we've done housing complexes with centralized heating. So you have about 30, 40 odd houses within the system. To do that with a straightforward HFC system is difficult because you're storing your water at 55. So now you need to reach the last house in line and you don't reach the temperature. You struggle to keep the temperatures that house require. Um, the benefit of CO2 is you can really get long runs out of your hot water because you can store it at 70, 80 degrees Celsius and you can mix it at the house, meaning that you can supply a lot of houses with the hot water and specifically the hot water that they require. So I am, and then especially in apartment buildings and hotels and stuff like that, I do see centralized heating becoming more and more a thing of the future. Um, and then as well in the heating side of life, or processing side of life, there is a lot of drying applications where predominantly normal heat pumps struggle to get to. Again, if you're looking at drying, certain drying processes require 80, 90 degrees Celsius to get certain things done, where you couldn't have done that predominantly with other refrigerants. You can do that with CO2. Um, and small steps. There are so many still steam boilers and stuff outside in the market, but nobody is looking at preheating. With CO2, you can get a lot of preheating. You can basically take your water requirements just before boiling. So you can almost take the whole preheating out of a boiler and just let the boiler do your steam generation side of life. That's a lot of savings as well. So yeah, I do think we're going to see a lot more of heat pumps. And interestingly enough, I think you mentioned it, Japan has been pushing out a lot of domestic heat pumps over the last few years. I mean, Europe is looking at a lot of centralized heatings. I mean, I don't know if if you've had a look at the largest CO2 installation worldwide currently is a centralized heating system of up to 50 megawatts done by Man, yeah, MAN. I hope I'm saying it correct. But I mean, they did a 50 megawatt centralized heating system. That's huge. I mean, that's basically literally
That
heating a whole village.
that is huge. That
um,
is huge.
but yeah, I do think actually, like, I don't know, if I were to put my money on something, I do think North America is going to be one of the biggest users of CO2 heat pumps in the near future.
Yeah, no, I believe so, and it's been here for a long time. Like, I think it's Sadin was here doing some water heaters on CO2. You know, so it's not even new to North America. It just is not popular. It's expensive. 20 years ago to get one of these systems, it's real expensive. But as more competition comes in, more people start to use it, starts to bring the cost down, and then there's more competition as well, which is going to really help promote CO2 in different applications like heat pumps, like chillers. And I like to see that because now it's bringing different technologies, different uniquenesses, and it brings other challenges as a contractor or a technician, as an engineer, to learn something new and not just keep doing it the same way it's always been done. And that's really
Yeah,
what I like about CO2 and why I like learning about it and why I even do these CO2 Mondays is because there's so much to learn about it. There's so many applications you can use it in, and it's fun for me to see these new technologies and the way it challenges us to make better equipment. Um,
Exactly.
so a couple more questions. You did lots of projects globally. You work with manufacturers, you work with consultants. What is some of the things that you can do for anyone here, participants? What can your company do to help some of them? If there's manufacturers on here, if there's contractors, how can Future Green Now or FGN can help?
Oh yeah, geez, like I say, we're a broad spectrum because we have experience and been involved in the A to Z of it. So I mean, I think the one thing that we're busy a lot with, so I can say what we're doing is we're doing for manufacturers or OEMs. We are helping them either develop a product or to end up being a product range within their product offering, or move their current products that's HFC based, and move that over with an alternative to CO2. So basically, I mean that's, and if you ask like how that means design of the system, um, manufacturing drawings, bill of material, supply chain support with sorting out supply chain, all that kind of stuff. And then um, end users, basically, what we and when it comes to industrial applications, is really we like to find what you mentioned, that bespoke um, solutions for specifically industrial applications. There's so many things you can do. It's like in industrial, you're never not just cooling something. There's always something else, and there's so many benefits you can get. It's heat reclaim, it's hot gas defrost. It's like really just squeezing every bit out of a refrigeration system to make the end user's facility as efficient as possible. Um, Installation drawings for installation support, um, that we can do. We can, if someone has a facility, we can specify what requirements or what CO2 systems they need, or what would be a good fit for their requirements. And if they are contracted, they need to install it, we can help with doing the installation diagrams, or teaching them how, like, what components to use, how to use it, when to use it, how to commission, fault find, that kind of stuff. So
I love
broad
that.
base, yeah.
Yeah, no, I know because we've been talking for years and you guys are just so awesome with that, so helpful and want to help. Anybody who wants to talk about CO2, you guys are in there. I love that. How can people get a hold of you or get in touch with you and your team if they want to learn more about your company or maybe they want to get your services?
Yes, I mean, you can find us at futuregreennow.co.za. So I mean, there definitely our contact details are on there, or you can reach us there. LinkedIn, we're all quite active on LinkedIn, so you can definitely follow us there. And then if there is any, like I say, any information or anything that you guys would like us to share, or anybody would like to find out a little bit more, yeah, feel free to reach out
Yeah, no,
on either of those platforms. Yeah.
I love it. And I really appreciate it. We're going to get into some questions here. If anybody has any questions, please throw it in the chat. We got a few minutes left here. And I know Daniel asked, you have any links I can look over CO2? Do you have any links on your website for on CO2 and stuff? Or
I can share some. I can look some about what specifically. There's a lot.
yeah, yeah, that's a pretty big question, Daniel. If you want to elaborate
Yeah,
on that a little bit more.
yeah. So I mean, there's plenty of information out there. So if you can, yeah, if you want to reach out, I can definitely see how I can follow you out. I mean, just to give you an idea, I mean, there's a lot of white papers published on CO2 that you can get for free by googling it, and luckily it's an easy search word. Just search transcritical CO2
Yeah.
or R744. You can't go wrong. You'll find something to read.
Yeah, head to Refrigeration Mentor's YouTube channel. I got a bunch of CO2 Mondays.
There you go. Yeah.
Awesome. Yeah, anybody else have any questions for Wynand? This guy is an expert, one of the leading global experts around the world about CO2. So you should ask the questions now. This is the time. This is why we do this stuff. Oh, we're gonna get your email again, Wynand. What's your email
Okay, let me just
address?
put.
He's going to throw it in the chat. And I will have this in the description file of this video as well as in the podcast, so you can get a hold of Wynand and his team, because it's very important to ask the questions. And if you think of questions after this, please reach out to me or Wynand as well.
There we go. I think that should get you guys to the right place. So I mean, yeah, I think so. From my point of view, like I think what I would like to specifically on CO2 heat pumps and chillers. Sorry, I'm like, if there's questions, we can go for it. But what's interesting is what's changing in the industry. I think is a lot of the sizes. So I mean, I know for argument's sake, there's some transcritical scroll compressors that's coming out that I really think is going to change the heat pump industry, and especially the chiller side of life. I mean, and then there's also the larger side of life. I mean, there is single screw compressors for CO2 coming out, which now you can have a single compressor, 1 megawatt CO2 chiller. I mean, I'm excited, and heat pump.
I know,
I
that's
mean,
awesome.
there is one running there in your backyard, Trevor.
Yep.
So, so I mean, I'm excited about these ones making it to the market and really creating new challenges and new solutions for CO2. Like, so there's a lot coming that's exciting, or to look forward to.
Yeah, no, and I'm excited about that because I know there's more, even more and more technologies like that transcritical scroll, like that screw compressor coming out, and as it gets more competitive, more of these manufacturers are going to start investing more money and more time
Yeah,
in research and development, especially when these come out, when they get launched and then they start to get mainstream. I know for sure more manufacturers are going to jump on board, and then
yeah,
regulations is going to push it as well, and it's real exciting times for
they're
CO2
very.
CO2 in industry.
I think that's what I like the most about CO2, that it is always this. It's always, I mean, in the last 10 years, and it's not going to stop soon. It's always been something new. Every year there's something new, or there's something different, or there's another way of doing it, or a new challenge. Like, it's never dull. It's always fun. It's challenging and very rewarding to be working with CO2 as a refrigerant.
Yeah. Well, I don't see any more questions in the chat. I want to thank you so much for taking the time to talk about CO2 heat pumps, CO2 chillers. There's so much more to learn from you. I'm sure I'll have you on again to talk about some other topics because you're just so knowledgeable, and I really appreciate your time today with us. Thank you so much.
No, I appreciate it. Thanks for having me.